Now, I want to welcome our next speaker. He is someone who has consistently produced really interesting applied research work in this field of real-time video AI. He recently published a project that extends the self-deforcing paper to create live video output. And previously, he's created projects like never-ending TV shows on Twitch. So please welcome Davide Locatelli on stage.
Hello, everyone. My name is Davide. I'm a computer engineer. I'm from Italy, and I have really a passion for world models and video models. What I really like about these models is the fact that you can literally simulate reality inside of this. And one of my first introductions to video models, actually to world models, was with this project. So with this project, I just found a world model which allowed me to simulate a game and inside of this model. And when I first saw this, I first started thinking, how can I actually go beyond borders with this? How can I actually make my own thing with this model? And what I decided to do was actually retrain the whole model on my game. And to do this, I had to basically make my own data set, figure out a way to make the data set the right way, a way to automatically collect a lot of information, stream it into the model training pipeline. And all of this led me to this actual playable demo in which you can play one of my favorite games, which is Mario Kart 64 inside of a model. And this is really what I like about this type of models, the fact that you can actually access the code. Of course, these models have to be open source in the first place, but you can access the code and bend them. You can break them. You can change how they work and bring them beyond the limits. So today I want to bring you through one of my other experiments of how we can bring video models to generate endlessly. Because these experiments, to me, are more of a learning way, a way to learn. After I did the world model experiment, when I retrained it, I got, at the end of the project, having much, much more knowledge about how the world models work in general. And I had basically no experience with training models before that. And I had to figure out everything I had to do by my own. So I want to bring you through another journey, which is making a model generate endlessly. And to do so, at the end, I want to show you problems that we get once we actually have endless generation. I want to show you these problems and my approach to solving this, and maybe give you new ideas on how these problems can be tackled. Let's start by diffusion. This is the easiest way to explain diffusion, in my opinion, with image diffusion. We just get some random noise canvas, and at the end, we run a process through it, and we get a defined image. So this is image diffusion, and it works in two dimensions, horizontal dimension and vertical dimension, height and width. What do we do is if we actually add a new dimension, the temporal dimension, well, we get video diffusion, because we now have a list of frames being denoised and generating a video. And this is really cool, and there are many models that are in high quality with this technique. The problem of this is that this temporal dimension is fixed. We can't, when we start the generation of the video, we already know how long it is going to be. So this is not a great fit, actually, for endless generation. It's like sitting down to write a story and knowing already that you're going to write exactly 100 characters. We don't really do this. This is not how, for example, we produce thoughts, and this is not how we actually write. The actual way in which we write is different, is autoregressive, and we lay each single word one by one, and every single word is built on top of the context of the previous one. For example, you could probably know that after this word is going to show ipsum, and so on and so on. So this is the autoregressive approach, and this is actually like how language models work. And this can be also applied to videos, and we can just use the output from the video, like the output from the last frame in the video, and use it to influence the next step of the generation. So we can have an animation of the butterfly opening its wings. And this is a great fit for endless generation. And I'm staying really high level in here, but there's actually papers that do this, such as self-forcing. And when I stumbled across this paper, which was about 4 months ago, I was super excited because it was super fast and it was a perfect fit for endless generation. Like, all the architecture that I described before was perfect. However, there was a problem with self-forcing. this number. This is the maximum amount of frames you can generate with self-parsing in their own demo. At least when I was playing with the model, this was the limit. And if you tried to change this number in the code, the whole thing was going to crash. And it didn't make sense to me, because why do you have to put such a limit on the generation? Like, why do you have to put a limit of 81 frames specifically? The architecture that I show is perfectly fit for becoming infinite. So why is there a limit? Well, in the paper, they actually have an answer to this. When you go beyond what the model has been trained on, beyond this limit, you start to see degraded quality. You start to see colors becoming more and more bright, the whole saturation in the image starting to increase, the contrast becoming more and more visible, and all the movements all start to become repetitive. So this was a problem in the paper. Like, this was already addressed in the paper, and it was perfectly fine, and it was reasonable, the fact that they didn't want you to generate such videos with their own model. It made sense. And so they had put basically this barrier. And once you were starting to approach the bad quality in the generation, you couldn't. Like, the whole model was going to stop. Well, as an engineer, I wanted to actually try this. I wanted to actually see these results with my eyes, and I couldn't. So what I did was basically breaking this barrier. And to break this, I just restarted the whole model. Once everything was finishing, when everything was approaching the 81 frames limit, my idea was to simply restart everything, load everything back in memory, reset every cache and every memory that the model have, and reinitialize the whole generation with the last step. And, well, this seems kind of stupid, but actually it worked. And I can show this result here. And we can see the same identical results as shown in the paper. We have these colors becoming more and more bright, movement becoming repetitive or almost disappearing. And yeah, this was really surprising as a result. But also, we can also see another problem that the paper was not showing, which is this flickering in the image. Every couple of seconds, there's a flicker. So this flicker, probably some of you might already recognize it as the fault of the VAE. And I want to cover what a VAE is, because I think it's really, really important in the architecture of these models. A VAE is basically a model that allows you to compress images into a smaller version of themselves. And why do we need this? Well, models are much, much faster when they run on compressed images, on much compressed images. And these images are not actually images, those are latents. These latents, we can really see them as humans, we can really understand them, but the models are really good at understanding what is inside of this. So these VAEs allow you to encode and decode images into this sort of new space. And we can think of this like image compression. You start from an image that is of a specific size, and we compress it down to a smaller version of it. Well, we can also go the other way around. We can also go from a small image to a large image, and in the same domain, with VAEs, we can go from a latent back to an actual image that us humans can understand. But when we do so, we have to invent new information. When we are increasing the size of the image, we also have to add stuff inside of it to fill in the pixels. So this is, we can apply all of this concept of image VAEs to videos. And when we do, so with videos, we have multiple images stacked one on top of the other. And we can actually go on one more dimension in this. We can compress not only on the vertical and horizontal dimension, but also on the temporal dimension. So we can compress multiple images in one single latent. And this is really important because it means that one latent will hold information not only about the quality of the image, like the colors and the shapes, but also about the motion. Each single latent will hold this information. And we can also go the other way around. We can decode. So from a latent that maybe a model has generated, we can go to a human-readable image or video. So if we actually want videos to work this way, we can pipeline this one after the other, do all of these decodings in a line. But there's a but. If we do this with no context one to the other, we get these results. Because each decoding is independent one to the other. When we decode the first image, the VAE basically fills in the colors in some way. But when we do the next decoding with the next latent, the model that doesn't have any context on the past will create a mismatch. It might generate randomly new colors inside of the new images that have been decoded because it doesn't have any concept of wanting to stay in line with the past. So how these VAEs actually fix this problem is by adding context, by linking these two passes one after the other with some context. And well, what I was doing stupidly was breaking this context. I was basically, when I was resetting everything, I was cutting this context down, and I wasn't allowing to be contextual. So after I understood this, and it took me a while to do this, but it's also helped me understanding how these VAEs worked, I ended up with these results, which is not loading. Yes, OK. So this is really similar to what is shown in the paper. And we have basically a video that can last for as long as we want. And we see the actual results similar to the paper. We see colors becoming more and more bright, movement becoming repetitive. Everything becomes kind of uncanny. I kind of had nightmares when I was doing all of this. So how do we do now? How do we go now about solving all of these problems, about quality? Let's think about what are the players in the game. What is actually being used to generate the next frames? And again, I'm going to simplify all of this a lot, but I think this is a good way to understand how these models works by doing these experiments. So each new frame is generated based on the prompt and the memory of the model. So we can, these errors that are starting to accumulate are eventually ended up somewhere in this image, either in the prompt or in the memory. And my first approach to this, in wanting to fix this quality issue, was by just trying to change the prompt and say that whenever it was starting to look like a Picasso painting with super bright colors, just go back to a realistic view. Go back to something that looks like something acceptable. And like I was literally begging the model, like asking it to please do something good, like go back to reality. But this, I knew, honestly, it was going to be a desperate attempt. And in fact, it didn't really work. So however, this experiment led me to understanding that the memory has a much, much higher influence on the generation. Like the memory has probably I mean, we're generating videos. We want videos to be consistent with the past. Therefore, the memory has a huge impact on this. And the prompt, sure, it can help you guide the whole generation towards a specific subject and towards a specific object. But the memory is what actually keeps the consistency in. What is this memory? Let's think about this. This memory is basically everything that the model has ever seen. Each time the model generates, and again, I'm super simplifying this, but each time a model generates a new frame, it puts it back into this memory, which is actually a KV cache. And all of the calculation done to generate the new frames are stacked on top of this new frame that has been generated. And we basically have a loop in which each frame helps generating the next one. So what happens now if a new frame starts to accumulate errors? Well, when this happens, these errors will go into the memory. And this memory will cause accumulation of these errors. And the new frames that will be generated will also show the same errors, and it will add even more errors to this. And this will cause basically a feedback loop in which each single frame that we generate will start to show these errors growing and increasing, as we were seeing in the previous video. So here we have an example of all of this. We have a cat that is not looking really good. And in this video, we can see a lot of frames being generated and showing this horizontal movement of the bushes. Again, I want to make a point on this again. Latents, so what the model sees, what the model understands are latents. And these latents also hold temporal information. They hold information about the motion of the image, the motion of the parts of the image. So in the memory of this model, we have a lot of information about these bushes moving horizontally. So when we go to generate the new frame, the model will desperately want to stay in its comfort zone with what is in the memory. And so each new frame will show the same motion, the same horizontal motion repeatedly. And we will never get out of this feedback loop. We will actually constantly add new errors to this, and we will basically never get to a high-quality image. So the model is super, super attached to its memory. But isn't there a way to actually free it, to free off these shackles that is the memory? And well, yes, there is a way. And this is like a kind of a innovative approach, which is just completely removing the memory, basically lobotomizing the model, removing all of the memory and the cache. And the results is impressive, because we can have this super degraded image suddenly become back an actually nice image with a nice cat that works and has actual motion. And yeah, this is really cool. And all of this is possible because the model doesn't anymore see all the errors in the memory. And therefore, all the frames that are being generated are able to become creative again, to add back new details and new colors instead of wanting to stay in this super drifted reality. So this is exactly what we were doing. We were basically having a super degraded image, and we were removing all of the memory, and the model was able to restore itself. What if now we couple this thing, this trick that we figured out, with also actually changing the prompt? Well, let's think about what the model sees at this point, now that we have removed the memory and changed the prompt. The model will see the last frame that has been generated as the starting point, and it will try, and it will start to invent new stuff based on the new prompt, starting, however, from the previous frame. So in here, we have an example of this prompt initially talking about a woman, and then we can just do all of this trick and say to show a cat. And the model will basically see the shape of the woman, but it will not understand anymore that this is a woman. It will actually see the prompt about a cat. So the video model will start to try and design and write and draw a cat. So it will look for the features in the image that are shaped like a cat, and will try to desperately move the generation towards something that represents this cat with all of these green flowers and bushes. The problem with this, so this actually was super powerful, but the problem with this was that it wasn't consistent. Sometimes I was running these experiments and I was getting these perfect transitions. Other times the model wasn't listening to my changes at all. And other times I was getting completely different scenes, like a huge cut in the generation. And I couldn't really understand why this was happening. Like, I was desperate. I was spending nights trying to figure out why this wasn't consistent. And then I just started brainstorming with a friend. And he just suggested, maybe it's a concurrency issue. Maybe the moment in which you do this cut, these memory cleanups, maybe those are important. Maybe you have to be careful when you do that. And he hadn't looked at the code at all, but he was perfectly right, because the denoising process is slightly different than what I thought. It is not just one step. You don't go just immediately from just noise towards an image. What you do actually is slowly do multiple steps, and in each single step, you remove a small amount of noise. And it turns out that every single step in self-forcing is aided by the cache. Every step basically is influenced by the cache. So let's experiment. Let's think about what happens when we remove the cache early, like right at the start of this process that generates each new frame. Well, now the model only has a random image, has random noise, and the cache has been removed completely. So the prompt is still talking about a dog, but the model only sees this, actually, only sees random noise and doesn't have a context with the memory anymore. So each new frame will bring us towards a completely different scene that, sure, it will represent a dog, but it will be a completely different dog with no consistency from the past. What now if we actually don't remove this cache and we actually start to perform these steps using the cache? Well, we can see that we go towards a more consistent image that is matching what is in the cache. But what if we remove this memory, this cache, at the end, like at the last step? Well, now the model will be able to be creative, to complete the missing parts of the image with whatever it wants and whatever we want to prompt it. So for example, here I changed the prompt saying to show the dog with the mouth closed, and the model was able to actually become free and represent this new information with creativity. And all of these experiments that led me to figuring out how to restore the quality and control the self-forcing model allowed me to end up with this cool demo in which I could basically morph this animal in many other different shapes. And the cool thing about this is that now, using self-forcing, we have endless generation, we have quality that doesn't degrade because we are removing the errors from the memory constantly, and we also have control. And I didn't have to retrain the model at all. This was just from experimenting with the model, looking at the architecture and playing around with the code and figuring out how it was working. And yeah, this was really cool. And I have also another demo I can show you. This is a funny thing because it shows how the fact that you have to be really good at prompting the model. For example, if you say the rocket takes off, you will constantly see in a loop the rocket taking off. So the model is super good as actually showing you how the takeoff works, like showing this to you. However, since the prompt is constantly saying about the takeoff, this will happen in a loop. And this is not actually how a takeoff works. So yeah, and I think that doing all of these experiments allowed me to understanding how these diffusion models work and led me to other intuitions that, I mean, probably those now are not really anything interesting, but 4 months ago when I was just playing with this, I was just experimenting and having my own ideas. So I thought, what if we just start with our own image and we put ourselves in the middle of the denoising process of self-forcing? So we add noise to an image and then we denoise with a new prompt. What happens now? Well, we have a video-to-video editor in which we can make video realistic, for example, by saying in the prompt to make it realistic. And again, this is just using the self-forcing model without retraining it in any different way, just using the model and changing the architecture. So yeah, I want to share everything with you guys because I think that playing around with these models actually at the code level and understanding and having intuitions about how all of these models works is super interesting. For example, I want to mention another super cool paper that came out really recently called Long Live. And this is super cool because I want to make an analogy. What I was doing was basically removing the memory from the model just to make sure that the new prompt would actually have an effect on the generation. And what Long Live does now is instead of throwing away all of this memory, it is just reprocessing it all completely using the new prompt. And by doing so, it can assure the consistency, but also it can make sure that the model actually reacts to your inputs in a nice way. So yeah, these are all the problems that you get when you're making a video generation model endless. You have to solve quality degradation, and you have to add controllability to this. And I wanted to show you with this talk the fact that you can actually find solution to this problem in a different way, in a more creative way, by looking at the code, playing around with this, having intuition, finding new solutions, and seeing where this leads you. So yeah, I would like to thank Eric for hosting me here, and yeah, thank you guys.